Camera is next to it. Just a brief. So warm greetings to everybody. I think most of you know her, some of your lab mates and some of you are probably her friends. Okay, so I'll not take too much time introducing her. So as you see, the topic is about carbon nanotubes. And she'll tell in one of the first slides that it's a wonder material recently introduced, but she's even more recent than that. I think good things come in small packages. So is rénukā. Direct after her bachelor's, she was admitted from NIT Raipur to IISc, and within 5.5 years, she's been able to complete her PhD thesis. So it's a really nice thing. As you know, this is a colloquium. A lot of people interchangeably use these words: lecture, talk, colloquium, defense, etc. But the word colloquium itself comes from the same root as colloquial, which means that it has to be informal and interactive. So that's what I'd expect from all of you friends, as well as people who are familiar with her work as well. See, this is a stage where she's giving finishing touches to her thesis, though it's very well published already, and of course has a lot of good peer reviews, and so it's well accepted. But nonetheless, any final suggestions which can probably make it a little better than what it already is, that will be most welcome. So I would like suggestions as well as questions. Some, of course, to help her enhance her thesis, but also if it helps understand better for yourself and probably for the rest of the group and those who are online as well. I would like that. And just feel free anywhere in between also. I hope it's okay with you to raise your hands and ask the question. I think you'll be following up with questions. People raise their virtual hands on Teams. That's how we'll go. I'd also like to tell a little more about the topic itself. Apart from carbon nanotubes, this is about the variational asymptotic method, and some of you have worked on the VAM. You know how tough this particular thing is, more from the point of view of a steep learning curve that we have, and compared to most other topics, even in our own fields of investigation. But once you're there, you really see the power of this method, and that's what she will showcase in her talk. Not only has she learned this very tough method so soon, but also combined it with another tough method, which is essentially the strain gradient approximations, which is again not very trivial. And to combine these extremely difficult concepts and apply it to multi-scales, starting from the nanomechanics of a single isolated carbon nanotube all the way to both beams and plates. So most PhDs in VAM are either only beam-based or only plate-based. So it's amazing that she has been able to do both the nanomechanics and take it up towards micro beams and micro plates as well, as you shall see in her results. And this she has done with not only for combined loading cases like bending, torsion, extension, etc., but also she has brought up geometric elastic instability, which is buckling. And you'd see the flexural buckling results as well, which is also published. And in this context, I would like to thank immensely her mentor, a former NM cadet, somebody whom I've known for 15 years, Professor Satish Kumar Anasuya Ponuswamy of City University of London. Is he there? Yeah. Okay. So we have Satish on Teams.
Hi, Professor.
And, hey, Satish. Yeah. Nice to have you. So he's been with her in this journey almost throughout the PhD, and her work will reflect a lot of his intelligence as well, not just artificial intelligence as Rajesh works on, but the actual natural intelligence. And to take it a little back in history, I would also say that there is one commonality that rénukā shares with my dad, and that's a birthday. even she doesn't know about that. And talking about dads, her dad is really popular in the Raipur region for enabling the higher education of a lot of tribals in the Chhattisgarh state around Raipur. And I'm sure she will take this forward in a big, big way. Talking of dads, and I should not refrain myself from talking about academic dads and granddads. So this work on VAM emanates from Berdychevsky, a Russian researcher who worked in the US. And from him, my advisor, PhD advisor, Dewey Hodges, learned this method and then imparted it to me, myself to Satish, and Satish to Renuka. So it's like a Guru Parampara that is going on, and things are becoming better and better in terms of the capabilities and the wider range of applications that we have for this particular methodology. But we see that when you go to very small length scales, as she is in the case of carbon nanotubes, there are a lot of local effects which come in, and therefore the non-local effects, in other words, stress and strain at a point are not dependent only on each other, but on a region which is beyond that, and how large is to be explored through what are known as material length scale parameters. And this is what she does through this particular work, and then incorporates them in the model along with VAM in order to take it forward. And so that's how it goes. The reason I mentioned Hodges is this work is actually seeded in my own PhD thesis, where you will see, in fact, some figures from that thesis as well, which is a thin-walled circular tube. Because when I started my PhD, of course, carbon nanotubes was an infant, and very few of us heard about it. But we were working on thin, hollow circular cylinders made of generally anisotropic composites. So very difficult when the nonlinear behavior and the buckling, local buckling, was to be tackled over there. This was actually an additional topic that I was doing on my PhD after having worked on thin strips, which innocuously, very simple geometry, but has the complexity of both closed cross sections as well as open cross sections. And then as an additional work, we just wanted to work on this thin-walled circular tubes. And I was kind of stuck up on this, and she'll probably relate to that as well. For a few months, I had absolutely no results. And then I dreamt, literally dreamt, not in the sense of what Abdul Kalam calls as dreaming, but just before my deep sleep, in my rest on my bed, I just dreamt of a Ganesha with a trunk. And of course, immediately after that, within a few days, I was able to crack that problem. Of course, my advisor was a staunch Christian missionary on campus, explaining the Bible to people far and wide, including the students. And therefore, I couldn't talk to him about Ganesha. I told him that I dreamt of an elephant's trunk, and then I was able to crack this particular problem. Witty as he was, immediately he said that, "Oh, Dinesh, then we ought to apply this for a funding from National Geographic." So that was how it went, and eventually this was well published, and also some of our former PhD students worked on it. Another reason this day is special is not just for Renuka, but for our lab, because she's our 10th PhD from our lab to offer the colloquium, and the first lady PhD candidate, and in that we are really proud of her. Of course, we should have had many more, and hopefully she'll be the beginning of many more female students that we will have. Though, of course, we have had a large number of masters, ladies who've done masters, and also interns, and an intern, a male intern from Georgia Tech was one she guided as well. So I should talk about her other capabilities as well in terms of mentoring students. And also Renuka was awarded the prestigious IISc award to go to Airbus and work with the head of the materials division over there. She was there for about 6 months. And she was also one of the first to have a comprehensive exam virtually during the COVID period, and she was successful in her very first attempt. So it's been a remarkable journey. And also the 2020 Open Day, I think she was one of the lead organizers, presenting a lot of things for young kids, probably very much similar to her dad, made it very, very exciting for a lot of invitees that we had at that point in time. Many of our previous 9 PhDs from Georgia Tech are all academics, professors in IITs and various other universities. We have had, of course, a few joining companies, so probably only one, and one who started his own company. And Rénukā will soon, as many of you will know, be joining Airbus. And Airbus, just this International Women's Day, celebrated their 1,000th women recruitee in India, and she probably narrowly missed that, or she would have been the 1,000th. But of course, she knew that news quite early, and let's wish her all the best. And as I said, this is a colloquium, so please feel free to interrupt and ask any questions. No question is silly until it is answered, so don't feel like if you're asking something that you don't know, what would others think and things like that. It would actually help her when she explains it to even more strangers or novices or beginners in this field, for her to start explaining from much more basic perspectives. So before I pass on the mantle to Rénukā, the mantle goes actually in this relay through Satish. So if Satish would like to say a few words, please do, Satish.
Thank you. Thank you, Professor. It's early morning for me today in London. First of all, thanks, Rénukā. You've been an excellent student to work with. Can you all hear me? Can you hear me? Is it?
Yes.
Yes.
Okay. Great.
I think the volume was a little low.
Okay.
I hope you heard
me a bit louder. Yeah. Is it okay now?
Yeah.
Okay. Great. Okay. Thank you, Professor, for the nice introduction. Very comprehensive. And I think I would like to take this opportunity to offer my advance congratulations to Rénukā. It's been a sheer pleasure working with you, Rénukā. You have been such a dedicated and a very sincere person to the work, which I appreciate and admire a lot. So thank you for being such a wonderful person, and I'm sure you'll go to great places in your career, both personally and professionally. So I wish you all the best. And needless to say, you have done a great work, especially not taking a traditional approach, because people have used variational asymptotic method for classical structures. However, what you have done is slightly different, in which you look into structures that are of nanoscale, which means you have to take the strain gradient approach or non-local approach, which no one has ever done in the WAM-based literature. So in that sense, it's a first of its kind work. So congratulations for that, and I'm sure the work will be well received by the community. Yeah. So without taking much of your time, I'll leave the floor to you, and congratulations again. It's been a pleasure.
Thank you so much for guiding all the way through. Good afternoon, everyone. Today I'll be presenting my
Just make sure she's at the center of that.
So today I'll be presenting my PhD topic, asymptotic modeling of carbon nanotube and carbon nanotube reinforced composite structures using strain gradient formulations. So I'm a member of the NMCAD Lab, and I have done this PhD work under Professor Dineshkumar Harursampath and as my mentor Satish Kumar sir. So the whole this was working. No, but if you stop sharing, then that will do. Just a minute.
Most of the presentation. It's fine.
It's fine.
Just to confirm from the audience, they're able to see both.
Yeah.
Ask us.
So is everyone able to see the screen?
Yes, the screen is shared and I can hear you.
Okay.
Okay. It's okay. This one is tight for.
Thank you.
You need to go into the vector.
You're sharing the screen.
I'm not sharing now. So
Sharing.
okay. Window. We do.
Yes.
See this is. Use the mouse. I use the Sorry for the delay. So I'll be presenting my work. Moving on, we have divided this whole talk into, as usual, the introduction, objective, methodology, results, and the summary and the feature scope. So basically, what we'll be starting with a carbon nanotube model, the development of carbon nanotube model in RAM and the buckling studies. Then we'll move on to a beam model, which is a RAM-based strain gradient model. As you can see, that is the novelty of this work. And we have done bending studies on that. And moving further, we have developed a plate-based model, again a RAM-based strain gradient model. And for that, we have done buckling and bending studies also. So starting with carbon nanotubes. So carbon nanotubes, they are recently discovered wonder materials by Ijima. They were discovered in 1991. And depending on the number of tubes and the geometry, they can be classified as single-walled, double-walled, and multi-walled. They are known for having very high Young's modulus, high tensile strength, they are light in weight, and they have high aspect ratio. So these are the mechanical aspects of their properties. But apart from these, they are also having superior thermal properties, very good electrical properties, making them good for multifunctional applications. So when I say superior thermal and electrical properties, it is in comparison to the composite materials which we are using in aerospace applications. And usually those materials don't have a good thermal and electrical properties. So because of this functionality, we can use carbon nanotubes and ensure that the structure has an added functionalization. And it has various applications ranging from biomedical, NEMS, electromagnetic shielding, lightweight composites, and even structural batteries. So these are the properties of the single-wall carbon nanotubes, wherein the thermal conductivity ranges from 1000 to 4000 watts per meter Kelvin. The tensile strength is around 90 to 120 gigapascal, and Young's modulus is around 500 to 1 terapascal. And the electrical conductivity, you can see it's quite good in 10 to the power 6 to 10 to the power 8 Siemens per meter. And for multi-wall carbon nanotubes, it's slightly less. So these are some of the experts of how carbon nanotube have been used in literature in applications regarding electrochemical application, wherein they can be used to trap the electrochemically active particles and used to give an electrochemical added functionality to a structure. Similarly, on charging and discharging, how carbon nanotubes behave. So this is some added functionality which we can use with carbon nanotubes. Moving on, since we deal with structures, we need to understand continuum mechanics. So continuum mechanics, it treats a body as a continuum. A continuum can be defined as a continuous and homogeneous substance or material, which can be described by smooth functions and equations without reference to individual atoms or molecules. Because since we deal with larger length scales, we are okay with not understanding what is happening in the molecular level. And then this assumption comes into place that stresses at a point depend on displacements at that particular point only. And this is applicable to meso and macro length scales. And all the existing theories leading to structures, they are derived from here, like Euler-Bernoulli beam theory or Timoshenko beam theory. But a problem starts to occur as we move to smaller length scales like micro and nano length scales. Now, since in today's world, we are going into smaller structures, we have nano-based structures and micro-scale structures, sensors, actuators, and all. It becomes imperative to go and understand how these structures can be modeled, even in a continuum framework, because we have to study their structural aspects as well. So here is a representation of how the time scale and length scale varies for the different structure length scales. So you can see here that for atomistic levels, we have that the length scale is also small and even the time scale is also very, very small. But as we move on, we deal with larger length scales, and of course the time also is time scales are also larger. So continuum mechanics has this particular applicability range. And so now, because we are having a problem of how to model micro and nano structures, we come into the non-classical approach. So basically, it can be of three types. There is a non-local theory, which is given by Ehringen. So here in the non-local theory, again, the stress, it not only depends on the displacements at a particular point, but even on the neighboring point displacements. So this is a newer defined, new definition of stress, which is taken into the non-local theory. Then we have higher order gradient theories, which include modified couple stress theory or strain gradient theory. And here they include the gradients of the strain also in the strain energy definition. So the classical strain energy definition just is up to the first term, but this higher order strain gradient theory, they consider the gradients of the strain as well when defining the strain energy functional. And then we have a combination of the two, which is the non-local strain gradient theory, wherein the stress, it is taken from the non-local theory, and the strains and the higher gradients of the strains are also taken. So these are the commonly used theories in literature, which comprise the non-classical approach. But why to have non-classical approach? As I said, in reality, any material or any structure, it has intermolecular interactions. And the basic assumption of stress locality, it fails for smaller length scales. And material is definitely not a continuum in reality. And we have that various attractive and repulsive forces exist between these entities. And it can be seen that they will affect the deformational behavior when we go to these smaller length scales. So right now what we are trying to do is we are coming back from materials, we are going inside to compounds, molecules, and then trying to understand what is happening at the molecular level. So our model is moving from millimeters to micrometers and even the nanometer scales. And just to know, like, what are the ways to use CNTs in composites? So the most commonly used method is matrix modification method, wherein CNTs are just dispersed into a polymeric matrix, and that is then cured and used as composite structure. And there is one more newer way, which is the grafting onto fibers. So this is a normal composite where you have carbon fiber reinforced into the matrix. But instead of having a normal carbon fiber, we have the carbon nanotubes grown all around the carbon fibers. So this helps to increase the functionality of the carbon fiber, and they also help to increase the transverse properties. Then there are aligned CNTs reinforced in laminates. So this is just a larger scale of using carbon nanotubes grafted in composite. So this is used for specific applications like improving the interlaminar shear strength or delamination properties of composites. So the strain gradient theory, it was first given by Mindlin in 1965. And the strain gradient theory, it states that the strain energy of any material, it is not only dependent on the stress and strain, but also on the gradients of the strain. So this approximation, it originates from the idea that, again, that stress at a point in continuum is not only because of the deflections or deformations at a particular point, at that particular point, but also on the displacements at the neighboring locations. So the strain gradient theory defines these following higher order strain tensors: the dilatation gradient vector, which comes from the fact that it represents the change in the volume at a particular point and the gradient of that change in the volume. So strain associated with that. Then we have the deviatoric stretch gradient tensor, which is the gradient of the strain associated with the stretching of the material at that particular location. Instead of like when the volume change is kept constant and you have the only the change in the stretch changes are encountered here. And then we have the symmetric rotation gradient tensor, which is again a gradient of the deformations occurring due to the rotation at a particular point in the continuum. So corresponding to each of these strain tensors, we will have these stress tensors, and associated with each of these gradient vectors, we'll have a material length scale parameter. So here we can see L0, L1, and L2. They are the additional material length scale parameters which come into picture in this strain gradient theory. So the material length scale parameters, L0, L1, L2, they are a very important part of the modified strain gradient theory. And they are introduced in these elasticity problems in addition to the Lamé's constant, which is the classical elasticity constants. So the physical meaning of length scale parameter is that it provides a representative size of the strain gradient effect zone in a material. So to what length scale the effect of these gradient vectors are valid in the material, that is defined. And it is not a constant. It depends on the material as well as the geometry of the structure, and it can be experimentally calibrated. So Khurshidi et al., they demonstrated the size dependence of these material length scale parameters for different materials. So it was found that if for epoxy, if you have a thickness of epoxy beam in range of 20 to 115 micrometers, the length scale parameter was 17.6 micrometers. And usually the L0, L1, and L2, these length scale parameters are taken to be equal. Just for simplicity, in most of the literature, that is the case, that all of them are taken to be equal and as denoted as L. So again, for copper, if we are taking a copper wire, which has a circular geometry, for different diameters, you will have different material length scale parameter values. And in case of nickel, if you are having a different beam thickness, you'll get different material length scale parameter values. So depending on what kind of structure you're modeling, you can use those length scale parameter values. Now the beam theories. So we all know that classical Euler-Bernoulli beam theories and other beam theories, they describe the bending of the behavior of the beam by using certain assumptions, like that plane sections remain plane and the normal to the beam reference line, it remains the same after beam deformation. The cross sections remain normal to the beam reference line after deformation. But as we all know that this does not give the exact solution, like it does not represent the beam completely exactly. So that's why there are modifications to these theories. Like Timoshenko, he modified Bernoulli beam theory and relaxed the normality condition by considering the transverse shear and other factors. And we also have higher order beam theories wherein they consider the shear, like the shear deformation theory and other higher formulations. So the variational asymptotic based beam theories, it does not have any ad hoc assumptions involved. It was given by Berdichevsky in 1979. And it is applicable for highly nonlinear problems, things which cannot be dealt with the normal beam theories. And it helps in saving computational cost and time. So that's why we are going forward with the variational asymptotic method. Our objective is to analyze CNT and CNT-based composites using analytical VAM-based approach. So coming to a literature review which we had done regarding carbon nanotubes and the strain-gradient formulations, it has been studied that the elastic rod model of carbon nanotubes, it has been studied using non-local theories, wherein different non-local parameters have been tested with molecular simulations to understand which fits better and to get the same results as the molecular simulations. Then modified strain gradient theory has been used for dynamic study of microbeams, and effect of CNT orientation and non-local parameter on bending behavior has been analyzed by Elthar et al. And further, by using modified coupled stress and strain gradient theory, the buckling analysis of microscale beams has been done, wherein the critical load buckling load predicted by modified strain gradient theory, it was found to be 3.2 times that what is predicted by the modified coupled stress theory, which is again higher than what we get in the normal classical approach. So it shows that we need to modify our theories, existing theories, for micro-based and nano-based structures. Then CNTs have been analyzed using molecular mechanics, and during buckling, a sudden formation of kink and sudden drop in stiffness upon buckling has been shown. And CNTs have been studied under torsion using continuum elastic shell models as well, and where nonlinear load deflection and load torsional curves and unstable post-buckling paths have also been obtained. So Silvestre, he did a study of buckling of CNTs under axial compression, bending and torsion using FEM and atomistic beam-based theory. So they highlighted the importance of CNT geometric parameters, which is the radius and thickness, on the critical load and strain measures. And this plot here, you can see it is derived from this paper. So there they essentially highlighted how upon buckling, the CNT cross-section changes from a circular one to a dumbbell shape. But this is an atomistic based study. And here we can see a distribution of what kinds of methods have been used in literature. And mostly you can see that MD and molecular structural mechanics and these non-local theories, they dominate the studying of elastic properties, bending and failure. And for strain gradient theory, we know that it was developed by Mindlin, and he identified additional material parameters other than Lamé's constant in classical elasticity. Now, the strain gradient theory by Mindlin, it was further modified by Lam et al. He introduced the modified strain gradient theory, where he reduced the material parameters from 5 to 3 for isotropic materials. And again, non-local strain gradient theory for shell formulations has been used for studying buckling of CNTs. And he was able to get very good correlation with the molecular dynamic study. And it shows the importance of how the non-classical approach can correlate to the molecular dynamics results as well. And further, CNT composites, definitely because of improvement in mechanical properties. As you can see, as we are increasing the CNT volume fraction, we are getting good increment in the elastic modulus and the bulk modulus. And even transverse elastic modulus and yield strength, flexural strength, all of these improve. Further, we can use CNTs to improve fracture toughness and interfacial shear strength in composites. And we have the multifunctionality aspect, definitely, that lightning strike protection, the electromagnetic shielding, piezoelectric sensors. So here this figure shows that this is a normal composite, and this is a composite with CNTs added. So this is the red zone, it shows the damage zone due to lightning strike. And this is the one wherein the CNTs are used. So definitely there is a lot much reduction in the damage zone once CNTs are used. And of course, we can see the range of the improvement upon using CNTs in composites. So the methodology which we are adopting in our work is the variational asymptotic method. And variational asymptotic method, that basically you can understand is it as combining variational methods and the asymptotic analysis. So RAM uses small parameters which are inherent in the problem definition itself. And they are used to study beams, plates, and also for homogenization studies. The basic concept is minimization of strain energy. So in the VAM analysis, the minimization, the asymptotic analysis, which is basically separating the terms in terms of different small parameters, it is carried out at the strain energy level instead of differential level, which is the usual case in normal asymptotic analysis. But in VAM, it is done at the strain energy level. And the order analysis, it forms an essential part of the model development. And VAM can be used to capture geometrically nonlinear behavior like brazier effect and trapeze effect. And it can also be used to study piezoelectric effects, delamination, electromagnetic, and other multifunctional properties. So here we have a basic flowchart representing the steps of beam analysis using VAM, wherein we start with a cross-sectional geometry, and we have a 3D elastic constant. So moving forward, we do the 2D cross-section analysis by using this order analysis and minimization of strain energy. We do the 2D cross-section analysis, from which we get the 2D warping and strain recovery relations. And again, we have the load and boundary conditions for the 1D beam. So from the 2D cross-section analysis, we'll get the 2D elastic and inertial constants, the basic stiffness matrix, which is fed into the 1D beam analysis to get the 1D displacements and strain and the stress results. And both of these are combined to get the whole 3D recovery analysis and to get the 3D strain and displacement relations. So we can model a whole 3D structure using VAM. The kinematic relations are represented here. So here is a schematic representing the undeformed and deformed configuration with the coordinate systems used for beams. So we have a reference line R and R representing the beam in undeformed and capital R in the deformed states. And the unit vectors V1, V2, V3 are in the undeformed state. And similarly, capital V1, V2, V3 are in the deformed state. And this is a general approach which is done in any VAM-based formulation. And we can relate the deformed and undeformed position vectors using the covariant and contravariant vectors. And we will establish a geometrically nonlinear 3D kinematics by using 3D strain definitions and deformation gradient tensor as given here. So then once we have established the kinematic relations, we come to the order analysis part. So order analysis is the most important part of the asymptotic study. And it is done at the cross-section analysis level for the beams. For plates, it will be done at the thickness level. And based on the geometry, the small parameters are identified and the problem is divided according to it. So the small parameters, they can be usually geometric or physical small parameters. And depending on different cross sections, we have listed out the small parameters used. So for rectangular cross section, the B by L, where the B is the width of the beam and capital L is the length of the beam. For circular cross section, the small parameter will be radius to length ratio. And for strip-like cross sections, where the order of beam width and beam thickness is very different, we'll have two small parameters, wherein the width to length ratio are the thickness to the beam width ratio. And similarly, for thin hollow cross sections, we will have radius to length ratio and thickness to radius ratio as the small parameter. And for physical small parameter, we consider the strain as the physical small parameter. And so the 2D strain energy components, they are segregated in terms of these orders. And the zeroth order analysis is done. So when you get the strain energy in these or in terms of these orders, you can summarize it as this, that U is U0 plus U1 plus U2, where U0 consider the lowest order terms in the strain energy. And for zeroth order, this is only minimized. And then moving further for first order approximations, we can consider U0 plus U1 and we can minimize those to get a variational formulation. So this is the whole flowchart explaining the zeroth order approximation, wherein you start with the position vectors, you get the covariant and contravariant vectors, and you obtain the deformation gradient tensor. Once you get the deformation gradient tensor, it is used to get the 3D strains, and order analysis is done based on small parameters. and the strain energy expressions in terms of small parameters are derived. Then we go for minimization of strain energy and we get the boundary value problem. And solving that boundary value problem, we can obtain the warping solutions. And once we have the warping solutions, again feeding those into the 3D strains, we can get the strain energy for the particular problem. So first of all, I would like to discuss the WAM-based modeling of single-walled CNTs. So here is the beam coordinate system, which was used to model single-walled carbon nanotubes. This is a hollow thin cross-section beam, and you can see the cross-section coordinate systems also, where the Ri is the inner radius and Ro is the outer radius. And so we are considering the single-walled carbon nanotubes as very thin and hollow thin-walled circular cross-section. These are the position vectors using which we'll get the deformation gradient tensor. And using the 3D grain strain definition, we can obtain the 3D strains. And here, as I discussed previously, the small parameters are radius to length ratio and the thickness to radius ratio. So we use Lagrangian multipliers to enforce global constraints. These are the global constraints which we'll be enforcing. So these global constraints, it ensures that there is no contribution of warping to rigid body deformation of the beam. So the first one ensures that there is no contribution of warping to rigid body deformation like extension. The other two represent that there is no rigid body contribution of warping to the rigid, there is no contribution of warping to rigid body like deformation due to bending. And the last one ensures there is no rigid body like contribution due to torsion. So we have the first order warping solutions as follows. And using these warping solutions, we can get the 1D constitutive law for the beam, wherein you have your 1D strains gamma 1, kappa 1, kappa 2, kappa 3 are the curvatures. And the A11, A16 terms, they are the normal stiffness terms which we get from the classical laminate link theory. And we have a nonlinear bending stiffness term here. So this nonlinear bending stiffness term, here rho is used to represent the bending curvature. So this means that the stiffness depends on the curvature of the beam, showing that once you apply a load, the curvature changes, the stiffness also changes. So there is a rapid change in stiffness of the beam as we continue on applying the load. So to solve this problem for the 1D beam, we use the 1D nonlinear analysis using finite element approach, and we use the mixed variational formulation. We have the definition of force and moment resultants as follows. And using the weak form of the mixed variational formulation, we can again relate the 1D strains to the displacements and rotation vectors. So here are the relations for the 1D strain and the displacements and the rotation vectors. And using all these definitions, we can get a generalized force and strain through constitutive law. And solving for gamma and kappa in terms of other measurable constant, we finally get this equation, which is then solved further. So now we have the equation to solve. Then we discretize the beam into n number of elements, and we use simple linear shape functions to get a set of nonlinear algebraic equations, wherein Fs is the structural component, and Fl is the load operator, and X is the unknown vector consisting of structural variables, which are given as follows. So here for each node, you will have these structural variables, which is F1, F2, F3, M1, M2, M3, and the 3 displacements and 3 rotations for each particular element and node, you will get that. So this is the whole structural and load operator. So applying different loading conditions, we can study the whole beam. So we studied CNT buckling using MAP. Here we have a axial buckling force versus transverse displacement plot. So here you can see that a simple compression, axial compression load was applied, and the beam up to some point, like the point A, the behavior was linear. But after point A, wherein the buckling starts, you will get a very huge transverse displacement, even for a very, very small infinitesimal increase in the force. So that means the instability has occurred and the structure has buckled. So corresponding to all these points, point A, point B, and point C, we also have the cross-sectional shapes of the beam, which is usually not obtainable using the normal beam theories. And here we can see that at the buckling onset, there is a slight change from the circular cross-section. And when you move to the points B and C, which is the post-buckling point, you will see that the CNT has a oval and a dumbbell kind of shape, showing highly nonlinear behavior. So this geometric nonlinearity in form of cross-sectional ovalization observed. This is like there. And we have this effect of nonlinearity. We have captured this for buckling loads. So the boundary condition used here was fixed free boundary conditions, where one end was fixed and the other end was free. And these are the CNT parameters used. And for the complete study, we have taken the length to radius and radius to thickness ratios in this order, in this range. And we have also done literature validation, wherein this first work, which we validated with, was a non-local model, non-local shell-based model. And we can see that the current work, it gives very good correlation with the non-local shell model for the 0.722 non-local parameter, and also with the molecular dynamic result, which was already used in the paper itself. And as we can see that with the increasing nanotube aspect ratio, the buckling load is decreasing. And further for this work by Lee et al., it is a molecular structural mechanics based approach. And here also the buckling load variation with slenderness ratio was captured. And we can see that the current work agrees well with the molecular structural mechanics approach as well. And more or less, it agrees more with the armchair configuration of CNT rather than the zigzag configuration of the CNT. And we have also validated with other methods, and also for combined loading cases of twist and compression, we have done the validation, and we were able to get good correlation with the literature here as well. And further, we validated a result with Abacus finite element model. So for this case, we use two different models using beam elements and shell elements. So for the beam elements in Abacus, it does not consider the cross-sectional geometry or the non-linearity. So that's why the beam model gives a very higher buckling load, buckling behavior compared to the shell model in Abacus, which considers the cross-section non-linearity and geometry. So you can see that our current model, it lies somewhere in between the shell and the beam results. And we have also done the parametric study, wherein we have seen how the buckling load varies with the radius to thickness ratio and the length to radius ratio. So here, keeping the thickness as constant and varying the radius, we have obtained this variation for two cases, one wherein the cross-sectional non-linearity is considered and one where it is not considered. So for pure axial compressive buckling, we can see that the variation is not much, but still, if you go to higher radius to thickness ratio, there is a higher difference between the buckling loads for the two case. And we have also done variation of critical buckling load with slenderness ratio, keeping the radius of the CNT constant. And we have that here, the difference between the cross-sectional nonlinear and no cross-sectional nonlinear case, it is quite evident. And for higher L/R ratio, meaning for a higher length of CNT, there is much more difference between the two cases. Then we have done the combined loading cases, where we have taken bending and compression into account. So again, for this case, first of all, we apply uniformly distributed bending load, and then we are incrementally applying the compressive load. So we have done again the parametric study, wherein the radius to thickness variation is considered. And as you can see, as the R/T ratio increases, the cross-section of the CNT also becomes highly nonlinear. So for smaller R/T ratios, there is not much difference between the two cases of no nonlinearity and with nonlinearity. But for higher R/T ratios, it shows that the bigger radius of CNT and with a smaller thickness, it will give you much more nonlinear behavior in the cross-section. And we have also done the how the buckling load varies with the applied bending load. So we can see that bending load has a larger contribution to difference between the cross-section ovalization and linear cross-section model. And here, yes, we can see that how the different bending loads for different for two cases, that no cross-section nonlinearity and cross-section nonlinearity have been compared. And this shows that bending load has a higher impact. And we have also captured the 3D deformations for the CNT for this case, wherein the gray model represents the undeformed CNT. And you can see the transverse deflection once the bending and compression has taken place. And here it's clearly seen that there is an ovalized dumbbelled shape of nonlinear cross-section of CNT. Similarly, we did the torsion and compression case. So here, instead of the bending load, we are applying a twist also. And again, for this case also, we studied the variation with slenderness ratio and the variation with the radius to thickness ratio of the buckling load. And again, the same conclusion can be derived that for higher length of CNT and for higher radius to thickness of ratio, there is larger difference between the nonlinear cross-section and linear cross-section cases. Similarly, we also got the 3D plots for the same torsion and compression case, where you can see the out-of-plane displacement also due to the twist. And we have also done a combined load case of bending and torsion. So here, instead of taking the transverse displacement, we have the rotation angle plotted with respect to the applied torque. And we have the similar kind of behavior. And we are using fixed free boundary conditions. So first we are again applying the distributed bending load, and then incremental torque is applied at the free end. And we have done the same parametric studies here as well. And the difference is evident even for the bending and torsion cases, that for higher L by R ratios and for higher R by T ratios, it becomes important to consider the cross-section nonlinearity of CNT while modeling them. And again, the 3D deformations for this case have been also obtained. So now we come to the strain gradient formulation for prismatic beams. So as we discussed previously, that the modified strain gradient theory, it's an extension of Mindlin strain gradient theory given by Lamb. And this is what we are using in our variational asymptotic formulation. So here we have the strain energy definition, and where we have the classical strain tensor, dilatation gradient vector, the deviatoric stretch gradient tensor, and the symmetric rotation gradient tensor. So we have segregated the strain energy in terms of classical higher first case, which corresponds to the dilatation gradient vector, higher second case, which corresponds to the deviatoric stretch tensor, and the higher third, which is the symmetric rotation tensor. So we start with the classical strain terms, which are given here, and then we move on to the higher gradient strain terms. And for that, we have obtained these particular expressions using the definitions of these gradient strain tensors. And then using that the definitions of the strain, we come to the order analysis part of the variational asymptotic method. So we need to consider what kind of small parameters can be used in this particular problem. So since we are taking a prismatic beam, we have the small parameter width to length ratio from the geometry of the beam. But now we also need to consider another small parameter, which we are introducing as delta L, which is the material length scale parameter to the length of the beam. And we have applied the following warping constraints. And so now we need to understand what can be the order for the material length scale parameters. So we have taken 3 different cases, wherein first case we are taking that the order of length scale parameter is much less than the order of the width of the beam. So for this case, we get the following strain energy orders. The classical strain energy order is given, and we have all the higher gradient strain energy associated with the gradient strains. They come to be of this order, wherein they have one order like higher than the classical strain. So this is one particular case. And we again took another case where the length scale parameters are taken to be equal to the beam length. So for this case, what we are getting is that these higher order energies, they have lower order compared to the classical strain energy. And for the third case which we have taken, which is the material length scale parameter order equal to the beam width, we have that the classical strain energy and the gradient higher order strain energies, they are coming to be of the same order. So we have chosen to go ahead with this particular case. However, we can also look in future with how these kind of variational problems can be solved further. That can be totally done. But currently we are going forward with this case. And we have taken these small parameters hence. So using those small parameters and the strain energy definition, we do the variation formulation, minimization, And we get the following governing differential equations and the boundary conditions, classical and non-classical boundary conditions. So solving them, we can move forward to the zeroth order warping solutions. And using the zeroth order warping solutions, we have obtained the zeroth order 1D constitutive law. So as you can see here, L1, L2, and L0, these material length scale parameters, they are appearing now in the zeroth order 1D constitutive law, which was not present in the classical model. So we are able to capture the length scale effects at zeroth order analysis itself. And if you assign the L0, L1, L2 as 0, we are able to get the classical results. So this proves that, yeah, the model is working fine. And it can be clearly seen that the length scale parameters, they appear in the bending stiffness terms and the twist stiffness terms. So these behaviors are much more impacted by the length scale parameters. And further referring to Hodges and using the Euler-Lagrange equations for prismatic beam in static state, we do the 1D beam analysis here, wherein the force and moment vectors are given as follows. And we have the 1D strain and curvature relations to the displacements and rotations. And we can get these generalized force and moment relations. So we did the literature validation of our work with Zhao et al. And we analyzed the variation of normalized bending rigidity, wherein normalized bending rigidity is the bending rigidity with respect to classical bending rigidity. And here we have the H by L star ratio, and L star is as defined here because that was the kind of formulation was used in literature. So we move forward with that. And this is for a zero Poisson's ratio case. And we also plotted the difference between the current model and Zhao et al. For different Poisson's ratio. And moving on, we did the first order approximation also, wherein the zeroth order warping solutions, they were perturbed to include one order higher terms. And then we get the first order warping solutions doing the same variational formulation. And again, we get the 1D constitutive law. So here again, the same kind of behavior is there, wherein you have the material length scale parameters appearing in the twist and the bending stiffnesses terms. But here, an addition is that you have a Poisson's effect coming into picture here in the first order analysis. So the Poisson's ratio effect is coming here. So this is different from the first order VAM analysis in that there only the twist stiffness term is affected with the Poisson's effect. But here, bending stiffnesses terms are also being affected. So we using the results, we have obtained the bending deflection of cantilever epoxy microbeam, and we have varied the thickness of the beam to study how the bending deflection is varying. So this is the boundary condition and the geometric parameters used for a study and the loading conditions. And here you can see that for a thickness of 10 micrometers, you can see that the classical results, they are giving much higher bending deflection, and the current work, which uses the strain gradient model, it gives a lower bending deflection, showing that the beam has stiffened, or at micro scale, the beam behaves in a much more stiffened manner. Similarly, if you move to 20 micrometers of thickness, the difference between the classical and the current work, it reduces. And again, if you keep on increasing the thickness of the beam, the difference keeps on reducing, showing that as you increase the length scale of the structure, the difference between the classical and the strain gradient model, it reduces. We have done the same thing for the simply supported epoxy microbeam, and we have applied a distributed, uniformly distributed load. And again, the same kind of behavior can be observed here also, that starting from 10 micrometers thickness of the beam, you will have a huge difference between the classical and the current work, wherein as you increase the thickness or the size of the structure, the difference keeps on reducing. So this theory we have then applied to a CNT-reinforced nano-composite microbeam, whose geometric parameters are as follows. And we used Voigt's homogenization rule of mixtures for estimating the composite properties. And the material properties were taken from Vaccaro. And here we get these bending deflections. So this we are using the first order results to get these bending deflections. And here we can see the variation with respect to the material length scale parameter L. So it's starting from 0, where we have the maximum endpoint deflection because that represents the classical case, moving to 5, which is the same value as the thickness of the beam. You can see how the endpoint deflection is varying for different beam coordinates and for different material length scale parameters. And this is done for 3 different volume fractions of the CNT, which are given as follows. So yeah, when we go on increasing the volume fraction, again the stiffness of the beam is increased, and that is combined with the strain gradient theory to give a much more stiffened beam. Now we come to the strain gradient formulation for plates. Again, here we start with the same kinematic relations, but here for plates we have the following position vectors in deformed and undeformed configuration. We obtain the deformation gradient tensor and move forward to the 3D grain strains. And here for plates, the small parameters which we have taken is the plate thickness to the plate characteristic length, which can either be the length or the width. And we have the material length scale parameter to the length ratio. And the following warping constraints have been applied for the variational formulation. So we have taken the orders based on the classical Van plate model, that the H by L small parameter taken to be same order of the strain, and delta square is a bookkeeping parameter here. And again for this also we have tried to analyze different orders of the length scale parameters. So here instead of taking the like for beam we consider the beam width, here we are considering the plate thickness. So we have taken first case wherein the material length scale parameter order is very less than the order of the plate thickness. So we obtain similar kind of behavior wherein the higher order energy, it is of a higher order than the classical strain energy. And for the material length scale parameter equal to the length of the plate, we get a lower order of strain gradient strain energy. And for the same order as the thickness of the material, thickness of the plate, we get both of them to have the same order. And we have taken this particular case and moved forward with our formulation. So we get the following governing differential equations and boundary conditions. And these are the 0th order warping solutions. And we have so this is the classical 0th order stiffness matrix. And here we have the strain gradient 0th order stiffness matrix. So we can see that we have material length scale parameters appearing again in the bending stiffness systems and the twist stiffness systems. So again, we can derive the classical solutions once we assign L0, L1, L2 as 0. And the length scale parameters, they are appearing in the bending and twist stiffness terms. And moving further, we do the 2D nonlinear analysis for the plate, wherein this is the representation of the plate geometry that we have taken. And these are the boundary conditions which we have considered. And these are the relations for the boundary conditions which we have used. So we did a literature study for this as well, wherein the bending deflection with respect to plate thickness for all edges simply supported case was studied, validated with Akos et al. For the strain gradient case, and we have got a good correlation. And similarly, for different B by A ratios of the plate, and we studied 2 different boundary conditions, all edges clamped and all edges simply supported. And we can see there is a good agreement with the current work and the literature. So for both of these work and moving forward, we are considering a 8 by 8 element mesh here. So now we have studied the bending deflection of all edges clamped epoxy microplate for classical model and for current model for different plate thicknesses. So the first graph has considered 15 and 20 micrometers of plate thickness, and we have applied a distributed load on the plate. So here you can see how the difference between the classical and the current work is. And as we move on to higher thickness values of 30, 45 and 60, 75 micrometers, the difference reduces. We have also obtained the 3D bending deformations of the epoxy microplate for the current model and for different boundary conditions. H and the plate thickness and the material length scale parameters are kept same in all of these models. So you can see the least deflection is given by the all edges clamped case, then the all edges simply supported, and the clamped free 2 edges clamped case, it gives the higher deflection. And we have also done a first order analysis of the plate model. So here in the first order analysis, the transverse shear terms also appear in the warping solutions. And further, we get a nonlinear stiffness matrix for the first order case. And that is used as an input in a nonlinear 2D code to get the bending studies to do the loading studies. So here we have a comparison plot of bending deflection, classical and the current strain gradient model under all edges clamped case. And as you can see, because of the nonlinear stiffness terms which have been obtained in the first order, the deflections are very, very high as to what we got in the zeroth order strain gradient model because of the nonlinearity which comes into play here. But still here for the classical case, the deflections predicted are very high compared to what has been predicted by the strain gradient model. We have also done buckling studies wherein we have considered the parameters h by L, like the variation with respect to thickness and material length scale parameter ratio, and variation with different beam plate width and thickness ratios. So here we can see for zeroth order how the buckling load varies as we are increasing the plate thickness. So as you can see for h by L equals to 1, there is a huge difference between the buckling load for classical case and current case because it is a smaller structure where taking the effect of strain gradients becomes very important. But if you increase the thickness to 5 times of material length scale parameter, the difference between the classical and current model, it reduces. Similarly, as we go for a higher A by H ratios, wherein H is kept constant and A is varying, we can see that as the plate size increases, the difference between classical and current model, it goes on reducing. Similarly, the same study has been done for all edges clamped also, and here also the similar kind of behavior is seen. And we have applied this model to a CNT-reinforced composite study, wherein unidirectional distribution of carbon nanotubes is considered, and a Voigt's homogenization rule of mixtures is used to estimate the CNT properties, and the following properties have been taken. And here we take 2 different cases for A by B, A and like the plate width to thickness ratios, 50 and 40. And we have considered 3 different volume fractions, wherein the plate thickness and material length scale parameter is kept same for all the cases. And we can clearly see that for a smaller thickness, plate width to thickness ratio, you'll have a smaller deflection, which again is small for a higher CNT volume fraction compared to a lower one. And if you go on to A equals to B equals to 50H, you'll get a higher deflection. So that is done here. Further, we have also done some parametric studies wherein we are varying the H by L ratio from 1 to 5 for different CNT volume fractions and for different boundary conditions. And we can see that the normalized displacement, the slope for the normalized displacement, it reduces, showing that the effect of having a higher thickness leads to much more closer to classical results rather than for a thinner plate, we'll have much more impact of the material length scale parameters. So this has been captured here for different CNT volume fractions. So to summarize the whole work, we can say that we have studied carbon nanotubes using VAM, and we have accounted for the nonlinear cross-sectional deformation, and we have highlighted its crucial role in the premature failure under buckling and in combined loads as well. And we have proposed a nonlinear modeling method using VAM and FEA, and that it provides a much more engineer-friendly way to study nonlinear behavior of carbon nanotubes and other nanostructures as opposed to atomistic modeling methods, which might take much more computational effort and time. And a novel beam model incorporating both zeroth order and first order, integrating the modified strain gradient theory into VAM framework has been developed for prismatic beams. And the bending behavior has been analyzed, showing a stiffening behavior of the beam. And the beam dependency, bending stiffness dependency on Poisson's ratio at first order approximation has also been shown here. And a novel plate model, again integrating the strain gradient theory into VAM framework for both zeroth order and first order analysis has been developed. And the influence of length scale parameters on the geometrically nonlinear behavior has also been captured in the first order approximation. And we have studied buckling and bending cases. So there is also ongoing work of development of a non-classical model for standalone CNT using modified couple stress theory, and the extension of this non-classical model to study the delamination in composite lies. And further, we can extend this work to include the effect of various non-classical boundary conditions and their physical significance, and extending the study to vibration and other dynamic analysis. And we can extend the study to incorporate multifunctional aspects of CNT-based composites. And since we have developed a strain gradient model, we can further include the development of a non-local strain gradient model for beams and plates. So these are the publications from the PhD work. And these are the references which I have used. Finally, I would like to extend my heartfelt gratitude to Professor Dineshkumar Harursampath for always being there and supporting no matter what. And Professor Satish Kumar sir for being the best mentor there can be and always coming up with solutions and steering in the right direction. Professor Ramesh Gupta for his wisdom and guidance, especially in the plate models. And Professor R. Narasimhan, Professor Anindya Dev, Professor M.R. Bhatt, and Professor Joseph Matthew, who were the panel for my comprehensive exams, and they helped with their suggestions and feedback. Professor Swarnendu Sil of Maths Department for helping with the intricacies of variational formulation while modeling the strain gradient formulation. IGSTC and Airbus for providing an incredible opportunity. My parents and my siblings for always being there for me in even the worst times. And my lab mates for helping out in every possible way they can. And my friends for making the time in IISc a very good one. Thank you for listening.
You are giving the very good presentation. That one is very from the industrial point of view. Where it is using right now this carbon nanotube concept in aerospace industry.
So I have, with my work during Airbus, I have seen people trying to incorporate these carbon nanotubes for thermal protection systems, and they are also trying to use them for sensors. So they have certain sensor-based applications wherein very small microwave structures are used. So instead of using another material, they are trying to incorporate carbon nanotubes into these sensor models. And also, mostly they're looking for multifunction applications to improve the current aerospace structures. That is there.
In one of the slides, you given that rendering something.
Lightning.
Of that.
Yes, yes.
So suppose our main rotor blades are critical loads they are carrying that. Suppose in case of thermal, some damage, different kind of damage will be there. So avoid that type damage, I think that we can use that. That is right.
Yeah, so even for thermal, we can use it because they are known to have good thermal conductivity. So they can reduce the damage area if you're using a CNT-based composite. So the damage area can be reduced comparatively to conventional.
If you consider a cocoa can, a cocoa drink you get, it's a can. It's a thin shell and hollow shape. How imaginative is your carbon nanotube to this big cocoa? And just for imagination purpose, I'd like to know.
Like you're giving example of a cocoa can.
Yeah.
Similarly, you can give example of a straw.
If that is so, then while doing bending, local crippling becomes a very big parameter. Local shells, if you hold a cocoa can, you compress it, local becomes completely crippled before the whole buckles. Here you have shown a complete buckling load, which is very similar to column buckling. Local crippling doesn't have any effect, or is it something completely different off the shelf?
So this buckling which we are applying a compressive load. So as you can see, it starts as a local level, right? It starts at a local level. The buckling starts at a local level.
That leads to local crippling in shells, in metallic shells.
Yes.
Whereas here, crippling or warping or nothing of that sort of thing. It is just that the tube is changed its dimension to from circular shape to dumbbell shape. That's all.
No, so those plots which I have shown, it is not after all that deformation has happened. It is before, like at the buckling onset, what I have shown. Those plots which I have shown. It's not after all the subsequent deformation has happened.
So do you mean to say that it is before the crippling itself?
Yeah. So what I have been able to capture here is at a local buckling level. So if you try to even go for higher like deformations, it becomes a highly non-linear case. At this step. So even the we cannot capture that 3D, like it's not highly effective that how we can capture that 3D model. If that is what you were trying.
No. Carbon nanotubes are more stiffer in comparison to metal. Metal tend to buckle. Carbon nanotubes don't. They break. Is it anything that I was just trying to? It's just a no. Conditional question or anything that was just trying to imagine when you said carbon nanotube and then crystal shell and metallic shell will triple and then everything will become like paper when you compress. Cripples and compressors.
Yeah, so don't consider those subsequent levels of buckling. Just the initial local buckling has been considered here.
Good work. Excellent.
It's a very good question. In addition to what she already answered, the very, very important point, because there are many different modes of geometrical instability that can occur, including both local as well as the global that you mentioned. And here, unlike in a Coke can, we have something that is okay, the properties of the carbon nanotube are different in different directions. So it's true that the CNT stiffness is very large, but also the geometry is also much more thinner geometry that you have compared to if you compare the thickness to the radius.
Right? Yes.
So I have done precisely what in my thesis what you had asked for, parametric study related to when the crippling will occur first and when the global buckling will occur first. Depends on a lot of these material properties. So what I did is I identified two ratios of the different material properties along with the geometric features built in. And when you compare these ratios for certain ranges of these two values, you will see that crippling occurs before buckling.
Yes.
Yeah. And in some cases, the buckling occurs before crippling. So, of course, that was not work related to carbon nanotubes, but it's for a generally anisotropic material, which can be used to make those thin tubes. So, using the properties for the case of the carbon nanotube, we can actually substitute that there and get the results. But my work directly is not applicable for carbon nanotubes because of the non-local effects which occur, which are very, very significant, as she pointed out in the beginning of her presentation, which is the huge value addition that she has made, a non-trivial value addition. Because without that, this which is applicable, my theory, which is applicable for larger length scale models, cannot be directly applied for the smaller length scale micro beams and micro plates that she's doing.
That's very interesting, actually.
Absolutely.
Very interesting.
Right.
It triples and then he or she is saying it doesn't do it all.
Right. So you pointed out these two, the local buckling and the global buckling, what you call as crippling or wrinkling. But I have considered a third thing, which is the material failure itself. So these three, two geometric failures and one material failure, we see different curves which kind of crisscross. And so, certain ranges of these ratios of material and geometric combinations where one will occur before the other. And absolutely anything which occurs after that is of no significance because you are not considered failure, right? So you have to look at, for example, if the crippling has occurred, you have to look at a post-crippling,
post-crippling effects in the plate.
Exactly. So you have to do a post-crippling analysis in order to understand what happens after that.
Very interesting. Very interesting.
And that's also a very important point you brought about the lightning protection, especially in aerospace and not only helicopter rotor blades, but the entire aerospace gamut. That's a very, very critical problem. And to a large extent, CNTs are being explored for that. There are certain practicality limitations which are coming in terms of the uniform distribution of these, both spatially and also directionally and things like that. And also beyond a certain volume fraction of the carbon nanotubes, it becomes a little difficult to manage the properties, and also the overall properties may not show as much rise beyond a certain saturation value for the volume fractions. So these are things that people are working on. So it's more of a research problem. So it goes off on a slightly different track, but it's important, as you said, to be aware of the practical applications, which is in fact a great thing she did, because she started off, I mean, I call rénukā, another name for rénukā's perseverance. If you look at her first paper, which is a review paper, a very large paper, she has looked at comprehensively many different aspects of carbon nanotubes and how they are applied to various things. So this is something that we did in collaboration with Airbus as well. So the exposure she had for 6 months in the materials division in Germany really helped in shaping those things. So a point is very well taken, because I can feel for you. I mean, when you're working with Dhruv and many other helicopters, and seeing how this lighting issues can be resolved. And this is one solution, probably not there yet as a direct plug and play solution, but definitely as we go forward, I think this will become a solution, if not a standalone solution, but at least in terms of augmenting existing solutions.
That opens up a very large field of area, as we have in plate post-buckling. In this case, no, it is a plethora of.
Absolutely, yeah.
It just opens up a Pandora's box.
Can be just a stepping stone for.
That's what your future scope is fantastic.
She has built a huge, very, very strong foundation. From which a lot of things can grow. Yeah, absolutely. Well said. Any questions from the audience? No questions. You can ask them.
Would anyone like to ask any questions regarding the presentation or anything in general?
Hello, Renko. This is Arvind from the NAL. First of all,
hello,
it was
sir.
nice work.
Thank
I
you,
just because I missed initial few slides, so I have just query like you compared the results with the classical and some other theories. As you increase the thickness, the gap was reducing.
Yes,
So, like, have you checked at what thickness the both will give the identical results? Like classical with the theory. Any that comparison?
No, sir, actually not, because the thing is, if you're taking some value of material length scale parameter, there will always be some slight difference between the classical and the strain gradient results. Both the theories, they will coincide only when you take the material length scale parameter as 0, no matter how big the structure you're taking. The difference will be there no matter how minute, but it will still be there because you are considering the length scale parameters.
Okay. And second one, any experimental support is possible for this studies?
Maybe in future, yeah, it might be possible because people have done experimental calibration for different materials. But currently we have not considered that. We have just taken the literature results.
Okay. Thank you, Renko. All the best for your future.
Thank you. Any more questions?
From the live audience, no other questions. So thank you very much, Rénukā. It was a good job. Good job. Satish, would you like to add anything?
Yeah, I've been listening to the questions. I think you also came in to add another perspective to it. So I'm happy with it. Otherwise, I would have jumped in as well to add more information. Thanks for that. Well done, Rénukā. Great presentation,
Thank you, sir.
and keep it up. And I'm heading back to a composite lecture now to deliver. So I'll get some inspiration from the start. And then, so the lecture is in an hour. And I'm going to talk about failure of composites, not buckling, but more on damage. So wish me all the best.
All the best to you, sir.
We wish
Thank
your
you.
students all the best.
Thank you. Of course, the whole inspiration for composites for me started back in 2009. I told this billion times, but I don't get lazy in saying this again and again. It's all started from you, and that is where the inspiration started. So thank you very much, Professor Harursampath, for that. And you have been an inspiration for many, and will continue to be. Thank you so much.
Thank you so much for those kind words, Satish. You have come a long way since then. Thank you.
Thank you.
You can conclude.
Yes.
Thank you.
Thank you everyone for being there and listening to the presentation.
Thank you, Rénukā.
Thank you, sir.
In meeting.
Okay.
And